Process Technology. Unit 11. Catalysis and catalytic processes. Outline. The role of catalysis in the process industry. What is a catalyst? Catalysts and catalytic reactions. Characteristics of catalysts. Homogeneous and heterogeneous catalysts. Reaction and reactor engineering. Chemical industry manufactures products that are essential for creating and sustaining modern society. The chemical transformations necessary to make these essential products often involve the use of catalysts. The catalyst provides a reduced activation energy barrier to transformations and facilitates better control on selectivity. The development and selection of the right catalyst therefore can make a substantial impact on process viability and economics. Besides the right catalyst, it is essential to develop the right reactor type and process intensification strategies for effective translation of the laboratory process to practice. The role of catalysis in the process industry. Catalysis is of paramount importance in the chemical industry due to its direct involvement in the production of 80% of industrially important chemicals. Catalysts are involved in more than $10 trillion in goods and services of the global gross domestic product annually. It is estimated that the global demand for catalysts is more than $30 billion and a very robust growth is projected in the future. There is an urgent need to develop cost-effective and environmentally benign methods of converting natural resources into useful chemicals using highly efficient catalysts and employing cleaner methodologies. The advancements in catalysis and applications to the chemical industry are very significant and are responsible for cleaner processes. Replacement of the stoichiometric reactions by catalytic reactions and application of new catalyst systems and technologies to make the processes environmentally friendly, energy efficient, and globally competitive are current needs of the industry. What is a catalyst? A catalyst is a substance that provides an alternative route of reaction where the activation energy is lowered. Catalysts do not affect the chemical equilibrium associated with a reaction. They merely change the rates of reactions. Catalysts are classified in a variety of different ways. The commonly used classification by reaction engineers is based on number of phases, such as homogeneous catalysis. Catalyst and substrate are in the same phase. Heterogeneous catalysis. Solid catalyst and substrate is a gas or a liquid. It is important to combine the understanding of catalysis with key reaction engineering expertise to translate the potential of a catalyst in the form of a practically implemented catalytic process or plant. Any catalytic reactor has to carry out several functions. Bringing the reactants into contact with the active sites on a catalyst. Providing an appropriate environment, temperature and concentration fields, for adequate time, allowing for removal of the products. Catalysts and catalytic reactions. A catalyst influences kinetics of a process without undergoing any change itself. A catalyst does not alter the thermodynamics of a reaction. In simple words, a catalyst alters the route without altering the destination. See Figure 1. Figure 1. A catalyst allows a reaction to proceed through an alternative path. Here the route is the metaphor for activation energy, minimum energy for a chemical system to undergo a chemical reaction, and the transition state of a chemical reaction. The role of a catalyst becomes even more important when multiple reactions are thermodynamically feasible. In such cases, an appropriate catalyst manipulates the reaction rates in such a way that selectivity toward a desired product increases. Several factors and parameters influence the performance of a catalyst. The selection of a catalyst for an industrial process therefore depends on the role it is supposed to play. The effect of a catalyst on kinetics of the reaction needs to be understood in detail to get an insight about the surface chemistry involved that would help in the design of a specific catalyst. It is therefore important to understand the elementary steps through which a catalyst influences the overall reaction. Homogeneous catalysts typically form a complex with one of the reactants which eventually transforms it into the product after interacting with other reactants. The process is essentially similar to homogeneous reactions in the absence of a catalyst and is often controlled by mixing reactants and a catalyst species on a molecular level. In contrast to the homogeneous catalysis, in the heterogeneous catalysis, several additional steps are involved along with reaction occurring on the catalyst surface, such as external diffusion toward a catalyst pellet, internal diffusion toward a catalyst surface, molecular adsorption on a catalyst surface, surface reaction, desorption from a catalyst surface, internal diffusion away from the catalyst surface, external diffusion away from the catalyst pellet. These steps need to be understood to select an appropriate reactor and operating strategy. Homogeneous catalysis has the inherent disadvantage of lack of ease of separation of product and catalyst after the reaction. Because a homogeneous catalyst is completely dispersed in the reaction media, these systems face difficulties in separation or recovery of catalysts. Heterogeneous catalysis allows easy separation and reuse of a catalyst. A heterogeneous catalyst has active sites which are the centers of reaction. Once adsorbed either physically or chemically, the substrate undergoes a reaction and the product is desorbed, subsequently rendering the surface of the catalyst free for further activity. Characteristics of catalysts. Catalytic substances have a tendency to form complexes. A large number of substances that have been observed to show catalytic properties are from the 8 group and 1b group of the periodic table, which have unpaired d electrons. Another interesting property of catalytic materials is the small energy differences between valence shells, which lead to a number of oxidation states. The characteristics of a catalyst may be defined by activity, selectivity, stability, accessibility. All 4 terms refer to the favorability of a catalyst to form a product. Activity is generally found to increase with temperature. All the other 3 depend on a specific reaction. Ideally, a catalyst should undergo the same catalytic cycle multiple times without a reduction in its ability to influence the reaction. Selectivity of the catalyst is characterized in the following different ways. Chemoselectivity is when a catalyst favors reaction with one substrate in a reaction mixture over another. Regioselectivity is when a catalyst favors the synthesis of a product based on the position it acquires in the substrate. Stereoselectivity is a phenomena wherein a catalyst may direct a substrate selectively favoring formation of one stereomer over another if a substrate has stereogenic centers. Morphology and material strength are important characteristics of heterogeneous catalysts. The catalysts are manufactured in a variety of morphology like pellets, trilobes, and extrudates. The overall pressure drop and effectiveness of the heterogeneous catalyst depend on its size and shape. Resistance to crushing and attrition are also important characteristics that need to be understood in case of solid or solid-supported catalysts. Thermal characteristics and the range of temperature for which the activity would be the highest without compromising on the selectivity is an important factor in the selection of a catalyst for the specific process. The catalyst characteristics need to be appropriately accounted for, including activation as well as deactivation of catalyst, while designing a suitable reactor for carrying out catalytic reactions in practice. Homogeneous catalysts. Homogeneous catalytic processes are catalytic processes that occur in the same phase as the reaction medium. The homogeneous catalysts may be metal complexes or common reagents such as mineral acids. And they can be uniformly distributed in the bulk reaction mixture. Because in a homogeneous catalyst system each molecule of the catalyst is distributed in the reaction mixture, more active sites are available to interact with the substrate. Hence, the reactions proceed at milder conditions and lower catalyst concentration. Another advantage of homogeneous catalysts is the ease of understanding the catalytic chemistry because the mechanism of the reaction is only dependent on the kinetics and not on the diffusion rate. Homogeneous catalysts used in industrial chemistry generally consist of organometallic compounds. Compounds with a metal-carbon bond. The central metal atom is bound to organic and inorganic ligands. The catalyst environment can be easily modified to alter the catalytic properties by manipulating ligands. Transition metals play a major role in the development of these organometallic complexes. This is because of the availability of d orbitals of transition metals, which allow ligands to bond in such a way that they are available for further reaction. Heterogeneous catalysts. Heterogeneous catalytic processes are catalytic processes where the phase of catalysts differs from that of the reactants or products. Heterogeneous catalysis facilitates a large number of chemical reactions. The use of heterogeneous catalysts is gaining importance because of the following reasons. Because the catalyst is not in the same phase as the reacting molecules, it allows for a higher possibility of catalyst recovery and recyclability. Chemical bonds are formed with the catalyst either through physisorption or chemisorption during the reaction and broken after it to regenerate the catalyst, albeit with loss of activity in some cases. Solid acid catalysts are easier to handle in comparison with conventional mineral acids such as sulfuric acid and hydrofluoric acid. They reduce capital cost and also ensure material safety because they are less corrosive. Heterogeneous catalysts for bulk chemicals have been used since the beginning of the chemical industry, hence the processes and their roles in the mechanism of reactions are well understood in most cases. Many catalysts with acidic or basic properties exist or have been designed to synthesize particular species, which ensures product yield maximization. Mixed metal oxides, clays, zeolites, silica, alumina, zirconia, and heteropolyacids are a few classes of catalysts used predominantly. They can be modified to a large extent through impregnation of homogeneous catalysts or metals and structural changes. Microporous and mesoporous structures or sieves and honeycomb-like structures allow heterogeneous catalysts to be highly shape and stereoselective. A new stage of development in heterogeneous catalysts is aimed at using renewable feedstocks, environmentally benign processes, techniques for downstream waste reduction. Commercial catalysts are generally available in various physical forms such as powder, pellets, extrudates. A catalyst facilitates reaction through the formation of complexes with reacting species. The product formed does not have the tendency to bond with the catalyst, which implies the catalyst surface is regenerated. However, this is only partially correct. The surface and structure of the catalyst are modified with each reaction. For instance, in the case of a pure metal catalyst, surface roughness and crystallinity change, whereas in the case of metal oxides there is a change in the ratio of metal and oxygen. Pore size plays a major role in structure and therefore in catalytic performance, such as selectivity, stability, conversion, yield. Porous catalysts provide a large surface area, the ability to support varied chemical functionalities, the ability to form different networks according to the applications. Catalysts are classified into three kinds of porous materials. Microporous catalysts. Pore diameter is less than 2 nanometers. A typical example of a microporous catalyst is zeolite. It has a crystalline and well-defined structure. It has a silicon, aluminum, and oxygen framework, and water or another cation may be present in the pores. Activated carbon is also microporous adsorbent and has varying origins, thermal resistance, and porosity, depending on the method of synthesis. Mesoporous catalysts. Pore diameter is between 2 nanometers and 50 nanometers. Mesoporous solids are synthesized through a templating approach wherein surfactants are used for directing the structure. Subsequently, the surfactant is removed, and a mesoporous system is obtained that replicates the surfactant assembly. Macroporous catalysts. Pore diameter is greater than 50 nanometers. Macroporous material can be synthesized by a sol-gel method such as porous silica, alumina, and zirconia gels. Morphology of the catalyst would be governed by temperature and amount of solvents or reactants used. Activity is the rate at which a reaction proceeds in the presence of a catalyst. The activity of the heterogeneous catalyst depends on the reaction conditions, temperature, pressure, catalyst loading, the reactor conditions, flow rate, surface area of a reactor. Selectivity is the extent to which a catalyst promotes synthesis of the desired product over all the possible products, including those with lower free energy. Selectivity is dependent on time, temperature, and other reaction parameters. Another important aspect of the catalyst is possible catalyst deactivation. The most typical causes of deactivation of heterogeneous catalyst are the following: aging, thermal degradation, deactivation resulting from changes in structure, sintering, an increase in the average size of the crystallites due to coalescence of small particles on continued usage of catalyst, fouling, coking, deposition of high molecular weight carbon-hydrogen compounds or primary carbons on the catalyst surface. Poisoning. Inhibitory substances bind strongly to the active catalytic sites on the surface. The reasons for possible deactivation need to be understood to develop appropriate regeneration strategies. To prevent deactivation, promoters may be added. Catalyst characterization plays an important role in understanding and improving overall performance of catalytic processes. A substrate may be either physically adsorbed, physisorption, or chemically adsorbed, chemosorption, on the surface of a heterogeneous catalyst. The difference between the two phenomena needs to be explicitly understood. There are no bonds formed in physisorption. Only weak van der Waals forces are responsible for keeping the substrate on the catalyst surface. In chemosorption, there is electron transfer and formation of strong bonds between a catalyst and a substrate. This renders chemosorption to be a more selective process and leads to the formation of a single layer on the surface, unlike in physisorption where multiple layers may be formed with each adsorbed molecule of the first layer acting as a site for the next. The commonly available techniques of catalysts characterization are transmission electron microscopy, X-ray diffraction, extended X-ray absorption fine structure, reaction and reactor engineering. Reaction and reactor engineering involves establishing a relationship between reactor hardware and operating protocols with various performance issues. Reactor performance, conversion and selectivity, product quality, catalyst activity and life, stability and operability, safety, environmental impact, hardware and operating protocol, reactor configuration, size and shape, feed and exit nozzles, mode of operation, batch, semi-batch, continuous, startup and shutdown protocols, operating conditions, flow rate, pressure, temperature, flow regime, reactor internals, baffles, heat transfer coils, distributors. A process engineer is faced with a host of questions while establishing a relationship between reactor hardware, operating protocol, and reactor performance. The major questions being faced by a reactor engineer can be grouped into three classes. What chemical transformations are expected to occur? How fast will these changes occur? What is the best way to carry out these transformations? What chemical transformations are expected to occur? This question is in the realm of thermodynamics and chemistry. Knowledge of chemistry and reaction mechanism is helpful to identify various possible chemical reactions. Thermodynamics provides models and tools to estimate free energies and the heat of formations of chemical compounds from which the energetics of all the possible chemical reactions can be examined. These tools help a reactor engineer to identify thermodynamically more favorable operating conditions. How fast will these changes occur? This question of estimating how fast the thermodynamically possible chemical transformations will occur involves a knowledge of chemistry, reaction kinetics, and various transport processes like mixing, heat, and mass transfer. Analysis of the transport processes and their interaction with chemical reactions can be quite difficult and is closely connected to the underlying fluid dynamics. Such a combined analysis of chemical and physical processes constitutes the core of chemical reaction engineering. What is the best way to carry out these transformations? The first step in any reaction engineering analysis is formulating a mathematical framework to describe the rate and the mechanism by which one chemical species is converted into another in the absence of any transport limitations, chemical kinetics. The rate is the mass in moles of a species transformed per unit time, whereas the mechanism is the sequence of individual chemical events whose overall result produces the observed transformation. The first step of the reactor engineering is to select a suitable reactor type. In catalytic reactors, multiple phases are almost always involved. Several types of reactors are used for catalytic and multi-phase processes. The reactors may be classified based on the presence of phases, such as gas-liquid reactors, stirred reactors, bubble column reactors, packed columns, loop reactors, gas-liquid solid reactors, stirred slurry reactors, bubble column reactors, fluidized bed reactors, trickle bed reactors, gas-solid reactors, fluidized bed reactors, fixed bed reactors, moving bed reactors. Existence of multiple phases opens up a variety of choices in bringing these phases together to react. A three-level approach is used for reactor design and selection. Strategy Level 1 – Catalyst Design Strategy. Gas-solid systems. Catalyst particle size, shape, porous structure, distribution of active material. Gas-liquid systems. Choice of gas-dispersed systems or liquid dispersed systems. Choice of the ratio between liquid phase bulk volume, liquid phase diffusion layer volume. Strategy Level 2 – Injection and dispersion strategies. Reactant and energy injection. Batch. Continuous. Pulsed. Contacting flow pattern. Co-current. Counter-current. Cross-current. Mixedness of concentrations and temperature. Separation of product or energy in situ. Strategy Level 3 – Choice of hydrodynamic flow regime. Packed bed, bubbly flow, churn turbulent regime. Dense phase or dilute phase riser transport. Besides the considerations for selecting an appropriate reactor and mode of operation, several other factors need to be considered while designing a catalytic reactor. Some of the key issues are the following. Understanding gas-liquid and liquid-solid transport processes. Mass and heat transfer across multiple phases play a crucial role in the performance of multi-phase catalytic reactors. Understanding intraparticle transport processes. Mass and heat transfer effects are important even on a catalyst particle scale. Most of the catalysts are porous, and therefore species and heat transport within the pores of catalyst particles control concentration and temperature profiles within the catalyst particle, and therefore conversion and selectivity. There are several ways by which effective Thiele modulus is defined to account for different shapes of catalyst pellets and different reaction orders. Compensating inhibition, deactivation of the catalyst. Various possible reasons for catalyst deactivation were mentioned earlier. Catalyst activity may be reduced due to deposition of inhibitors on active sites. Inhibitors may be consumed in reactions unlike catalysts. The most commonly used strategies with which one may compensate for reduced activity of the catalyst are by reducing flow rate or increasing temperature to maintain conversion at the design level. Manipulate selectivity of the desired product. Several strategies for enhancing selectivity of the desired products have been proposed by the classical chemical reaction engineering approach. These include manipulation of operating temperature or temperature profile across the reactor according to difference in activation energies of competing reactions. High temperature is used if activation energy of reaction producing desired product is higher than reactions producing byproducts. Revision. Explain the role of catalysis in the chemical technology. What is a catalyst? How does the presence of a catalyst affect the reaction? What are the types of catalysis according to the number of phases? What are the functions of a catalytic reactor? List the characteristics of a catalyst. What are the elementary steps of homogeneous catalysis? What are the elementary steps of heterogeneous catalysis? What are the aims of the current development of new catalysts? What forms are the catalysts available in? List the advantages of the porous catalysts. How are porous catalysts classified according to the pore size? What is the size of pores in the microporous catalysts? What is the size of pores in the mesoporous catalysts? What is the size of pores in the macroporous catalysts? Define the term catalyst activity. Define the term catalyst selectivity. List the causes of catalyst deactivation. Explain each of them. List the techniques available for catalyst characterization. How catalytic reactors are classified according to the presence of phases. Give the examples of the reactor types from each of the groups. What types of reagent or energy injection regimes are used in catalytic reactors? What contacting flow patterns are used in catalytic reactors? What hydrodynamic flow regimes are used in catalytic reactors?